Good morning. We'll start with the first session, keynote speech. We have two excellent guests from the Planck Institute of Geoanthropology. Our first speaker is Dr. Renn, he's a historian of science, founder and director of the Planck Institute of Geoanthropology. His research focused on long-term evolution of knowledge and consideration of the historical dynamics that led to the global changes encapsulated by the concept of the Anthropocene. He investigates together with his team the structural changes in the technosphere that have given rise to the Anthropocene. So let's welcome Dr. Renn.
Yeah, thank you very much for the warm welcome, and I cannot but follow up on Professor Salasiewicz's remarks. It's a wonderful occasion to be here. And I want to say also very clearly, I believe in the Cheshire cat. I think the cat shouldn't disappear too quickly. We need you, and we need the formalization, and I'm sure it will get there. I want to say that as a moment. So thank you, Professor Park, for the great honor of opening this important symposium with our keynote, Jochen and myself. It's a privilege to be here at KAIST among such distinguished colleagues to explore together how we might redefine our understanding of the Great Acceleration. Your leadership in bringing together this remarkable international community of scholars reflects the truly interdisciplinary nature of the challenges we face. Living conditions on this planet are changing rapidly. Extreme events are becoming more frequent, more severe, and more persistent with anthropogenic climate change. Everywhere we hear, we read, or experience, record heat events, wildfires, droughts, and flooding. But this is not just about climate change. We are facing a dramatic transformation of our planetary environment. What are the facts behind this transformation? Here we see flashing before our eyes the bewildering complexity of our current situation. Precise measurements from atmospheric chemistry, soil science, epidemiology, ecology. Each fact rigorous within its discipline, but each carrying its own methods and uncertainties. This assembly of data confronts us with a fundamental challenge. We basically understand climate change, but we are just beginning to understand how everything is deeply connected. This interdependence is what the concept of the Anthropocene, introduced by chemistry Nobel laureate and Earth system scientist Paul Crutzen in 2000, is meant to capture. But how do we explore this concretely? How do we formulate this interdependence and make it tractable for research and for action? We have insights and precise measurements from various fields, yet we cannot easily synthesize this knowledge into coherent understanding of our planetary crisis. The fragments remain fragments, and the big picture is lost. In 2005, Will Steffen and colleagues from the International Geosphere Biosphere Program, IGBP, proposed an elegant solution. In our words, define a parsimonious set of variables, it's like the state variables in physics or order parameters in complex systems theory, that capture the essential behavior of coupled human Earth systems and their mutual feedbacks and study their behavior over time. This approach strongly resonates with us, and I believe with all of us. But the authors themselves recognized a fundamental challenge. This requires, they say, a new type of more integrated Earth system science that does not presently exist, but is evolving rapidly. They acknowledge that the science to accomplish this integration was still missing. This is precisely what belief needs re-emphasizing today. This recognition also motivated the founding of our new Max Planck Institute of Geoanthropology, dedicated to developing exactly this kind of integrated science. A first version of the iconic Great Acceleration Graphs appeared in the 2004 International Geosphere-Biosphere Program Synthesis Volume entitled Global Change and the Earth System, a Planet Under Pressure. But notably, the term Great Acceleration doesn't appear anywhere in that publication. The graphs were simply presented as, I quote, examples of changes in the Anthroposphere over the past few hundred years. The term Great Acceleration was actually coined a year later at the 96th Dahlem workshop in Berlin in June 2005, during discussions chaired by the late Will Steffen among social scientists, natural scientists, and humanities scholars. When in 2015, the group around Will Steffen published a paper entitled The Trajectory of the Anthropocene, the Great Acceleration, their claims had grown much stronger. In particular, the authors now explicitly link their concept to the geological Anthropocene debate, to which Jan was just alluding, and confidently stated, it is only beyond the mid-20th century that there is clear evidence for fundamental shifts in the state and functioning of the Earth system that are, 1, beyond the range of variability of the Holocene, and 2, driven by human activities and not by natural variability. End of quote. By 2015, Steffen and colleagues had thus created what they called an iconic symbol of the Anthropocene. 24 hockey stick graphs, as they came to be called, tracking Earth system and socio-economic trends from 1750 to 2010, which we now see on this slide. What began as an exploratory research framework in 2004 became, by 2015, evidence for formalizing the Anthropocene as a geological epoch. The appeal is obvious. If a clear temporal break, as postulated by the authors, occurred around the mid-20th century, this would provide important support for defining the Anthropocene. In the second, the Great Acceleration concept has become immensely successful and has been deeply entrenched in the Anthropocene debates since the 2015 reference article. A search in the bibliographical database OpenAlex reveals over 3,500 citing articles to date, likely an underestimation given the database incompleteness. The paper has a field-weighted citation impact of 59.62. That is, it is cited 60 times more than the global average for comparable publications. This success is perhaps not surprising, given that the concept resonates with a widespread conception of modernity. And I'm very happy that the second talk by Professor Umson will also deal with modernity, the theme of modernity. Charlie Chaplin's 1936 Modern Times, for instance, captured the human experience of industrial acceleration, workers trapped in the relentless pace of mechanized production. In 2005, sociologist Hartmut Rosa formalized this intuition in his theory of social acceleration, analyzing the interconnected nature of technological, social, and pace of life acceleration that characterizes modern societies. Rosa builds on Reinhard Koselleck's concept of acceleration time, Beschleunigungszeit, from his 1988 Critique and Crisis. The Great Acceleration concept participates in this longer intellectual tradition. Historian John McNeill established the empirical foundation in his 2000 book, Something New Under the Sun, arguing that, I quote, more has changed since 1900 than in all of human history before 1900. The 2004 IGBP synthesis echoed this. I quote again, the second half of the 20th century is unique in the entire history of human existence on Earth. End quote. From Chaplin's industrial worker to Rosa's acceleration society to the Great Acceleration, the narrative remains consistent. Modernity equals acceleration. But something else is astonishing. The great acceleration concept quickly evolved from an ambitious interdisciplinary program to something that can be called a defensive metaphor in the follow-up publication of 2024, entitled, and I quote the title, "The Great Acceleration is Real and provides a quantitative basis for the proposed Anthropocene series/epoch." Already in 2015, first methodological cracks had become apparent. Stefan et al. Then acknowledged, and I quote, "major challenges of incomplete and inaccessible data sets, changing methodologies and data coverage," and admitted being unable in most cases to check the reliability of underlying raw data since there is rarely more than one source, end of quote. Also, language about exponential growth was notably softened, acknowledging that many trends show power law rather than exponential behavior, and that correlation does not necessarily imply causation. Besides the critical reflection by the authors themselves, there were also some critical voices raised from the outside. Among them, that of the physicist Ron Nielsen, who in 2021 applied not a loose notion but a formal definition of acceleration and pursued a rigorous mathematical analysis demonstrating that, I quote, "growing rates of most data sets fit hyperbolic trajectories up to around 1960, at which point they depart into periods of decreasing growth rates," end of quote, proposing instead a great deceleration. The 2022 response by the Great Acceleration authors reacts to Nielsen's critique with a stunning retreat. Here you see the quote, "The term, i.e. Great Acceleration, was not intended for use in a precise mathematical sense, but rather metaphorically." We thus see a transition from a proposal for international scientific coordination to mere metaphor. They also softened their analytical categories, claiming that rapid increase would be more descriptive, but the term Great Acceleration is now entrenched in the literature. They even explicitly discourage mathematical analysis, stating, quote again, "mathematical analyzing the Great Acceleration curves fails to account for the complex array of socioeconomic drivers evolving over many centuries." Most remarkably, they argue that visual impression alone, i.e. simple plots showing changes in magnitude over time, remains sufficient to identify a rapid and unmistakable change since 1950. They claim that patterns are clearly visible in the data plots without statistical analysis. This essentially suggests that the unassailable truth of their claims should be immediately recognizable from the graphs themselves. We do not share this position. Instead, we want to return to the original 2005 approach, and I quote again, to define a few key indicators that capture the changing nature of human societies. But we want to go beyond mere capture. We want to explain this relationship systematically, using mathematical modeling and causal understanding of the feedbacks. We do not just want to describe the kinematics, but analyze and understand the dynamics of the Anthropocene trajectory. That's a term, by the way, that we find is an ingenious choice of terminology that we gladly take over.
Let us demonstrate our position by examining the graphs themselves once more. The selection of variables is sometimes dubious and has been changed over time without justification. For instance, the authors replaced number of McDonald's restaurants in the original graphs with global primary energy use. Everyone would agree it's a better choice, but no systematic methodology is offered for such judgments. Furthermore, the separation between human and Earth system variables is not always clear. For instance, marine fish capture and shrimp aquaculture are classified as Earth system indicators, yet these clearly measure human activities, not Earth system states. In the literature, we see a constant stream of new proposals to expand the data set by additional variables. We also believe that an expansion of the dataset is desirable, but such an expansion requires methodologically grounded criteria which the authors do not provide. It must always be clear that the goal is modeling the human impact on the Earth system, without systematic criteria for variable selection, without proper distinction between drivers and responses, without understanding the causal mechanisms. The graphs remain compelling visual narratives that resist, however, the analytical rigor needed for genuine systems understanding. As a matter of fact, the graphs do not take into account many of the known and well-studied interactions and relations between the variables displayed. Take, for instance, the primary energy use in the socioeconomic graphs and the atmospheric carbon dioxide concentration among the Earth system graphs. We know through bookkeeping the amount of fossil fuels burned to create the primary energy. We know the carbon content per fuel type and thus also the global annual carbon emissions. It is furthermore well known that at least for the last 60 years, the amount of these emissions that remain airborne is rather constant at about 47%. It is therefore absolutely clear why these two curves behave so similarly. The crucial question that science is currently addressing is whether the airborne fraction will indeed remain constant or rise because of a saturation effect due to ocean acidification. In this example, as in others, the great acceleration curves display as correlations what in reality are causal interactions. Many of these interactions are already understood, some in great detail, as we've just seen, others at least quantitatively, while yet others need to be investigated. The curves thus distract from the interesting variations in the data and those important interactions that are not yet fully understood. The graphs are very suggestive, but we need to move beyond visual suggestion to scientific assessment, from rhetoric to rigor. As a first illustration of visual rhetoric hidden in these graphs, we want to mention the issue of normalization. The great acceleration graphs share a striking visual feature that goes entirely unmentioned in the methodology. All graphs are scaled so that they end at approximately the same height in the final year 2010 in the updated dataset. This scaling convention is never discussed, justified, or even consistently applied. To be clear, the authors never explicitly claim that graph heights are directly comparable across panels, but this is precisely what readers do automatically, and what others have done when illustrating the great acceleration by superimposing all variables on a single graph, as we see here in a diagram by Lewis and Mastin. While the original graphs use what we might call a quasi-normalization, the suggestive visual presentation inevitably leads readers to interpret them as if they were properly normalized. This creates the visual impression of universal dramatic growth across all variables, but is this impression justified? Let us demonstrate this effect with 4 socioeconomic variables: nitrogen from fertilizer application, world population, world GDP, and primary energy use. Why we use this one data set will become clear in a minute. The top row shows these graphs using the great acceleration quasi-normalization to the last year in the data set. The middle row shows the same data scaled relative to 1860 values. The bottom row uses 1950 as the reference year. Notice how dramatically the visual narrative changes. When we normalize to 1860, we see why the 2010 normalization is so misleading. If one variable grows substantially over the period, like were to be in our case, which increased, I think, 183-fold, it visually pulls up all the other variables, necessarily creating the impression of correlated dramatic rise across all indicators. Remember, all three rows show identical data sets. Only the representational convention, that is, the scale ratio chosen, has changed between the rows. More provocatively, if you depict everything with reference to the same ceiling, of course everything seems to go through the roof next. Our proposal is to normalize instead to Earth system impact, which requires understanding dynamics and causal relationships. The straightforward principle is this. Equal visual changes should correspond to roughly equal Earth system impacts. We should move from visual suggestion to scientific assessment, from rhetoric to rigor. Perhaps the most striking methodological weakness lies in plain sight. The prominent dotted line at 1950 that appears across all graphs. Remarkably, this line, which carries the entire argumentative weight of identifying the onset of planetary scale transformations, is never mentioned, explained, or justified anywhere in the article. It is clearly there because of the coupling of the great acceleration to the geological formalization debate, which brought in the necessity to find a clear, definable temporal signal for the start date of the Anthropocene. Yet, without criteria for why the line belongs at 1950 rather than 1940, 1960, or any other date, or in fact, if it belongs in the graphs at all, it becomes scientifically meaningless. The line makes sense only if there is a related systemic discontinuity in at least some of the parameters. So let us look whether such discontinuities can be read off the data. On close inspection, we see of the 12 socioeconomic indicators, we must first strike out foreign direct investment, paper production, international tourism, and transportation, because the great acceleration data sets have no pre-1950 data for these indicators. Two more serious, water use and urban population, are modeled with well-behaved functions that are smooth around 1950 by definition. This leaves us with merely 5 indicators that could potentially show a signal in 1950. Let's briefly look at the global, the large dam data. The global reservoir and dam data set lists reservoirs with a storage capacity of more than 100 million cubic meters. In the 2015 paper, the Great Acceleration authors remarked, and I quote, "The number of large dams, however, has shown a strong leveling over the last 10 to 15 years. This will probably become a longer-term trend because the number of large dams that can be built is limited by the finite number of large rivers." Now, we agree with this assessment since it is clearly growth under constraints. If we fit a 3-parametric model of growth under constraints, the Richards curve, we see that the number of dams built over time follows this model extremely closely. If we look at the number of dams built per year in the graph below, we see that the deviation from the model behavior is best described as a wartime dip with post-war recovery, with only a minimal overshoot. Thus, while this variable has some kind of a signal around 1950, it is almost the opposite of what the authors would need in order to substantiate their great acceleration hypothesis. It can rather be described as a return to previous trends after wartime disturbance. So, to make a charitable argument, let's also omit this parameter with the counter-indicative signal. So what remains to establish the 1950 signal in the socio-economic tableau is a rump data set of GDP, primary energy use, fertilizer consumption, and population. We shall look at this rump data set in a minute. So We have here looked in some detail only at the socio-economic parameters. As for the 1950 line that also occurs in the same way in the tableau of the Earth system indicators, it's there supposed to indicate the moment when the Earth system leaves the Holocene envelope. That is, when at least many of the values start exceeding the natural patterns of variability during the Holocene. To expand and systematize the idea of natural variability within the Holocene Earth system as a whole would indeed be a great research project to pursue. But without such deeper investigation, which gives concrete meaning to the metaphor of the Holocene envelope, the 1950 line in the Earth system graphs can certainly not live up to the claims connected to it. After this critique, we now turn to our own analysis of what the data actually shows. Let's examine the 4 remaining indicators, our ROM data set, that could potentially reveal a 1950 signal. But first, a crucial correction. For nitrogen fertilizer, we must and do consider total nitrogen fluxes, not synthetic fertilizers alone as in the great acceleration graphs. For biosphere impact, the distinction between synthetic fertilizer and manure makes no difference. Both inject nitrogen into ecosystems in the same way, and synthetic fertilizer fluxes exceeded those from manure only as late as 2010. However, artificial fertilizer production via the Haber-Bosch is extremely energy intensive, using about 2% of total global energy. Future analysis should thus consider both time series. With these 4 graphs, now the overall picture emerges. Yes, something happened in the mid-20th century. The known post-war boom that was the historical starting point for the Great Acceleration thesis. Population, the baby boom, greatly increasing birth rates between roughly 1946 and 1964 before returning to deceleration. GDP, the golden age of capitalism, about 1950 to 1990. In 1950, we do not so much see acceleration, but stabilization, where extreme volatility disappeared and growth became consistently exponential. Energy, the golden age of oil, from roughly 1950 until the second oil crisis. We see a post-war recovery with high but declining growth rates, ending with the second oil crisis of 1979 and suggesting constraints are being approached. Nitrogen, the green revolution of the 1960s. Agricultural intensification driven by high-yield crop varieties and in particular use of fertilizer with consistently high growth rates. Taken together, these developments stand for the post-war boom. Of course, one could refer to this post-war boom as Great Acceleration. In accordance with the 2022 paper by the Great Acceleration author, where they effectively redefined the phenomenon as the more descriptive rapid increase. However, they also write the term is now entrenched, as we see. And this entrenchment, besides mere terminology, carries causal implications. Whoever speaks of Great Acceleration today also alludes to it being the root cause for our departure from the Holocene envelope. The concept's entrenchment in the literature has indeed carried forward the assumption that these mid-20th century phenomena were responsible for pushing the Earth system beyond Holocene norms, even as the authors retreated from strong analytical claims. In order to approach the question of whether the post-war boom is in fact the crucial process responsible for the onset of the Anthropocene, we can ask how a world would look like in which the post-war boom had not materialized. In other words, to probe the causal character of this explanation, it makes sense to engage in a counterfactual analysis. What are the assumptions of our counterfactual? In our case, we simply take away the post-war boom and ask what remains. This, of course, does not mean the world would have stood still, but that it simply continued the tendencies before the post-war boom and without the post-war boom. In other words, what would happen in such a world based on the data of our rump data set? Our method is straightforward. First, we calculate the mean growth rates from 1900 to 1950, before the golden age of capitalism. In the case of GDP, this average growth rate for the first half of the 20th century is 3.3%. Then we apply these normal growth rates also to the subsequent boom period, as if it had never occurred. In the case of the GDP, we thus counterfactually assume that the mean growth rate in the golden age of capitalism, that is between 1950 and 1990, never exceeded the average of the first half of the 20th century. That is 3.3%. The purple line shows the counterfactual trajectory for global GDP, which results from this capping of growth rates. What do we see? The absence of the golden age of capitalism would have merely postponed the growth we associate with the Great Acceleration. We would reach today's GDP levels only about 20 years later, but we would still be on essentially the same exponential trajectory. This reveals something crucial. The problem isn't the temporary rapid growth between 1950 and 1990, but the underlying continuous growth dynamic that has been operating for much longer. The post-war boom appears to be merely a modulation of such a more fundamental tendency towards sustained growth. We apply the same counterfactual analysis to primary energy use during the golden age of oil. Taking the mean growth rates again from the first half of the 20th century, in this case 1.8% per year, and applying them throughout the golden age of oil, that is from 1950 to 1979, we see a quite large effect. The energy use in 2022 would, in the counterfactual, have been about half of the actual use of primary energy. This counterfactual low energy scenario in 2020 corresponds to about the use of primary energy that we had in 1986. Quite a compounding effect. However, the same argument applies as before. We would be merely set back in time with regard to the actual developments. In this case, by 34 years, but we would nevertheless be on exactly the same growth trajectory. As a consequence, following the logic of the Great Acceleration authors, we would still have long left the Holocene envelope, even under the counterfactual conditions. That is, without the Great Acceleration. Our analysis points to the actual root cause of the transition to the Anthropocene. All the variables in the rump data set are consistently characterized by positive average growth rates over longer periods of time. Negative growth rates occur, if at all, only on limited timescales of maximally a few years. Such long-term positive growth rates are the signature of positive feedbacks. As the system variable grows, so grows the driver of the variable. More people means on average even more people in the next year. More energy expanded also means on average even more energy expanded in the next year. Higher GDP means on average even higher GDP next year. More nitrogen means on average even more nitrogen in the next year. While more people in fact beget more people, of course more nitrogen does not directly generate more nitrogen, and neither does GDP generate GDP by itself. But rather this happens through different causal feedback chains, which are, however, all of the same positively self-driving character. The actual growth rate is not so important because of compound interest effects. It will always lead to every limit, such as the famous planetary limits being exceeded. Whether earlier or later is not so decisive. The post-war boom is just a modulation of this underlying, let us call it, great growth. The post-war boom has brought us closer to the limits in shorter time, but we would have come there anyway, not too much later. To be sure, we are not claiming that a limited system can sustain unlimited growth. Negative feedbacks will necessarily set in, and we are already experiencing the first signals. We have not yet managed, however, to control and cut the positive feedbacks ourselves in a desirable manner, but feel the systemic limits through extreme events, pollution, biodiversity loss, social instabilities, wars, and pandemics. Intervening in such a complex system requires understanding its dynamics. While variables unfold over time, as shown in the acceleration graphs, the system's dynamics are based on interactions between variables. One interaction stands out as particularly important: the relation between population growth and primary energy use. Population growth is indeed the elephant in the room in the Great Acceleration discourse. Like primary energy use, most other global long-term changes in socio-economic activities are driven by world population growth, at least in part. In the most simple case of constant per capita resource use, population is just a multiplier. The overall resource use of 1 billion is 1 billion times the per capita use. Yet, this fundamental driver lurking behind most great acceleration curves remains systematically unmentioned and unanalyzed in standard presentations, as we'll see now. And essential system properties are thus overlooked. Where the great acceleration graphs have the population over time and the energy over time, we now look at the energy over population. This allows us to distinguish between demographic dynamics, which are covered by the left graph, and structural scaling patterns, revealing what the elephant has been doing all along. For our scaling analysis, we use double logarithmic plot of the primary energy use over population, which is remarkably different from the previous graphs. The reason for using this representation is the classical assumption of scaling theory. One wants to test whether a dependent variable, in our case the primary energy use, can be described as a simple power law of the driving variable, that is, in our case, where the energy is proportional to the population to the power of some exponent n. If such a scaling law applies, the graph in the log-log diagram is a straight line. Yes. The log-log graph resulting from the energy population data is clearly not exactly represented by a straight line, but comes close to it. This in itself is very surprising, since it means that the average per capita primary energy use is indeed systematically related to the number of people on this planet. This is not as we used to think about it, We normally see per capita energy use as dependent on historical processes connected with technology and society that unfold over time and not over population. We can even go further and look for more precise accounting of the data by a piecewise linear representation, so-called breakpoint analysis. The number of breakpoints is chosen such that with a minimal number of breakpoints one can explain the greatest variance in the data. In our case, this results in 2 breakpoints, one in 1919 and one in 1981, which divides our total time from 1800 to 2020 into 3 major periods governed by different growth regimes. These regimes are characterized by the exponents, which in the log-log representations appear as the slopes of the straight line segments. Before 1919, the slope is very close to 3. Between 1919 and 1981, the slope is almost 2, and after that it's approximately 1 1/3. In these regimes, growth is clearly described by the underlying scaling law with negligible noise on top of it. Before we come to an interpretation of these scaling exponents, we want to emphasize how very far-reaching and mind-boggling this result is. First of all, there are indeed sharp changes in behavior that can be pinpointed in time, but they're not to be found in 1950. Second, the trend is not rising. On the contrary, every transition leads to a lower exponent, meaning greater efficiency in energy use. That is, a certain percentage change in population after the behavioral break results in a lesser change in primary energy use, than the same percentage increase before the behavioral break. Referred to population growth, we thus see the opposite development to what is seen in the great acceleration graphs over time. The efficiency gain may not look like much, but remember, this is a log-log representation. Hence, third, the effect of this increased efficiency in energy use is enormous. We can see this by applying, again, a counterfactual argument. What if the primary energy use had continued to rise over population as it did throughout the 19th century, that is with a scaling exponent of 3, until today's 8 billion people are reached? As you can see on the slide, the energy use of 8 billion people would be an order of magnitude higher than it actually is, and we'd all be dead. Compare this to the modest factor of 2 we get in our earlier counterfactual argument about energy use without the post-war golden age of oil. To state it bluntly, whatever happened around 1919 had an immensely larger impact on the future trajectory than the post-war boom. If we are looking for systemic breaks, this is where to look for them. Also, the behavioral change resulting in the final segment, that is, in the time after the oil crisis, still corresponds to half of the primary energy use if compared to the counterfactual scenario that extrapolates the trend between 1919 and 1981, again, to today's 8 billion people.
How can we explain these dramatic findings? We do not know yet exactly, but we believe that we know where to look for a blueprint of an explanation, namely in biological systems. There is indeed a striking parallel. Just as we may be surprised that commonalities exist between such different worlds as those of the different phases of the 19th century industrialization and can be revealed by scaling laws, so can common structural patterns between different organisms in biology, from the mouse to the elephant, be revealed by scaling laws. The parallel is even closer as it refers to similar quantities: metabolic rate, which corresponds to primary energy use, and body mass, which may be seen as the counterpart of population size in our analysis. In biology, this relationship is captured by Kleiber's law, discovered in the 1930s. Kleiber found that metabolic rate scales with body mass raised to the power of 3/4, meaning that when an animal's mass increases tenfold, its metabolic rate increases only about 6-fold. This represents an economy of scale. Larger organisms are more energy efficient per unit body mass than smaller ones. But is it possible to also explain the breaks in scaling behavior as we observed them in our scaling analysis of primary energy use with regard to population? So not just the scaling, but also the breaks in scaling. Pursuing this question, we encounter an even more remarkable biological parallel. When we compare not just different sized organisms within one category, but fundamentally different types of organisms across the entire evolutionary scale, from simple prokaryotes to complex multicellular organisms, we also see dramatic shifts in these scaling relationships. This is where a groundbreaking paper by DeLong and others becomes relevant. They discover that as biological organization becomes more sophisticated over evolutionary time, energy efficiency systematically increases. Prokaryotes show superlinear scaling. They are energy inefficient. Protists achieve approximately linear scaling. Metazoans reach the familiar sublinear Kleiber scaling of 3/4. Each major evolutionary transition created new organizational structures that improved energy efficiency. There is, however, still one major difference. In the biological world, we see convergence to an economy of scale. The relevant exponents eventually fall below 1. In the social world, we also see a decline of the relevant exponents, but they are still larger than 1, corresponding to superlinear scaling. In other words, the technosphere is still far from having reached an economy of scale comparable to that of the biosphere. The comparison with biology gives us a crucial hint where to look for explanations of our breakpoints, in the network structures that organize energy flows. The three-quarter scaling in Kleiber's law, for instance, emerges from the constraint that distribution networks must reach every cell while minimizing transport costs, a geometric imperative that produces fractal branching architectures with predictable scaling properties. Consider our energy scaling, where primary energy use first scales as p cubed, then shifts to p squared. We can construct a simple network-based explanation. Imagine a growing population where energy creates connections between members. If each person contacts a fixed fraction of others, the connections in the network grow as p squared. If the energy per connection also grows with population, say because distances get larger, total energy grows as p cubed. But if new infrastructures keep the energy per connections constant, growth becomes p squared. We suspect this captures what happened with mass electrification after World War I, a fundamental reorganization of how energy flows through society, similar to the evolutionary transitions that changed metabolic scaling in biology. Hence, just as prokaryotes and multicellular organisms are truly different types, so are apparently the energy systems in the different historical periods indicated by our breakpoints. Let us come to our conclusion. In the face of the problems of the great acceleration concept that we have outlined, we propose to return to the original inspiration for this concept in the IGBP context. Just as the original approach sought to do, we intend to map the complex coupled human Earth system into a relatively low-dimensional state space and to analyze the system's trajectory through this space. But we are not just interested in the kinematics, but in the dynamics driving it. For variables defining the socio-economic subspace, we made a first start by examining how they are driven by population increase and are investigating what structural organizations and reorganizations account for the growth patterns over population that we have observed. We describe our approach as a macrodynamics of the coupled human Earth system. But we propose to reconceptualize under a different heading, not the great acceleration, but the great growth. What does it entail? Where Earth system models emphasize resolution and process detail, our macrodynamics approach emphasizes empirically testable, predictively powerful order parameters, trading spatial and process granularity for computational tractability and theoretical clarity. Crucially, the proposed approach is top-down, allowing us to identify the most consequential feedback loops first. Only then can one become actionable and implement appropriate measures. Even engineering negative feedback loops is, after all, conceivable. Our concrete analysis reveals that population energy scaling shows dramatic regime shifts at 1919 and 1981, representing fundamental reorganizations of how energy flows through human society. These transitions matter far more than the elusive 1950 breakpoint that has dominated the great acceleration discourse. The biological parallel is instructive. Just as evolutionary organizational transitions systematically improve metabolic efficiency, human socio-technical systems have undergone similar structural transformations. Yet, unlike biological systems that achieved an economy of scale, the technosphere still operates under superlinear scaling. We have not yet reached the efficiency that characterizes mature biological organization. As an illustration of the practical insights to be gained from such a framework, consider the global energy transition so necessary to mitigate climate change. Managing the shift to renewable energy requires coordinating both molecular flows, that is hydrogen-carbon compounds, and electron flows through electrical grids, just as biological organisms must coordinate eating, molecular energy acquisition, and breathing, electron transport through cellular respiration. Both systems require integrated networks that efficiently distribute energy carriers. From this kind of analysis, we may learn not just what transitions are needed, but how they should happen, how organizational innovation can enable efficiency gains comparable to those of biological evolution achieved. But this is just the beginning. We need much more data and much more analysis. For instance, we do not just have to look at our energy flows, but also at our material flows, of course. Our scaling analysis has revealed patterns we don't yet fully understand. Which actual processes are historically responsible for the regime shift in 1990? Which structural reorganizations drove the 1980-81 transition? How do other coupled variables behave when examined through scaling relationships, rather than according to time series? These are open questions requiring systematic data gathering across multiple domains and deep interdisciplinary cooperation. We are proposing the great growth as a cooperative international research program, one that can only succeed through the kind of collaboration originally envisaged in the IGPP program. We invite participants of this conference and this broader research community to join this endeavor. Indeed, we are eager to learn from the presentations that follows ours today, to understand what insights from different disciplines, different scales of analysis, and different regional contexts can contribute to building this research program. How such a program be structured? What data infrastructure is needed? What methodological innovations will be required? How can we create the institutional frameworks for sustained international cooperation? The original intuition behind the great acceleration concept deserves the analytical rigor we have tried to apply here. By moving from visual metaphor to mathematical analysis, from iconic symbols to testable hypotheses about feedback dynamics, from passive documentation to active identification of intervention points, we can transform the great acceleration's compelling narrative into the great growth explanatory framework. One that not only describes planetary transformations, but helps us understand how to guide it towards a sustainable future. So with this, we both, Jochen and I, will thank you for your attention, and we are looking forward to learn from you all in the following presentations. Thank you for your patience.